points that I want to make today. We're going to keep things very general. I'm going to try to see some cool stuff. I have 2 main points, and then I have a quest, and that quest is like the main quest of the course, the thing we're going to try to do. And by hopefully the end of the course, we will prove the main quest. I think last time I taught the course, we did it exactly on the last day. So the main quest and 2 points. And the first point, my first main point. Let's do number 1. Point number 1. Number 1. Everything is functions. This is the first point. Everything is about functions. Is functions. And to prove this point to you, I'm gonna take all the courses you gave me, and I'm gonna tell you why every single course is actually just about different functions. Every single thing you do in math is functions done in a different way. Let's see what you guys said for functions. So 24 people have answered. That's a good enough number. Okay. All right. Advanced analysis. Calculus is the most obvious one that is like plainly about functions on the face of it. A lot of people might say, okay, if there is a course that's about functions, it's calculus, but the other courses are not about functions. Combinatorics is a good one. In combinatorics, the functions are like permutations and things. So that one's harder to see, but it is actually about functions. So calculus, obviously about functions. Let's say obvious. This is the only time I will use obvious because the fact that calculus is about functions should be obvious. Of course, you're doing very detailed, like is it increasing, is it decreasing, like really specific things about the functions. Combinatorics is very subtly combinatorics. And I'll say like, e.g. if you count things, you are looking from a map from something like, if you say like, how many ways can I arrange these people in a circle so that Alice is not next to Bob because Alice and Bob have a feud or something. What you're looking for is functions that map something nice. So you're looking for maps, e.g. like permutations and things like that, that map nice ordered sets to nasty things. And you're looking for asymmetries, things like that. A good example is, there's a problem like how many different ways can you make a necklace out of some beads? Well, there's a map of rotating the necklace, and you can use that kind of thing to do these counting arguments. So combinatorics, even though I think maybe of all the courses seems like it's the least about functions, is actually still about functions. They're discrete functions that map kind of the counting different things by the number of maps that do certain things and things like that. So combinatorics secretly about functions. What other ones? Differential equations. Differential equations, of course, another one that is quite easy to see. It's about functions. Differential equations. Let's see, I guess everybody's probably taken the first ordinary differential equations class. Has anybody taken partial differential equations? Okay, lots of people. So differential equations is, again, it's about functions. And it really is the flavor of, I'm thinking of a secret function that has these and that properties. Can you tell me which functions work? So this is, again, another one where it's like finding the functions that satisfy the things you want. So how to find specific functions. How to find the specific functions we are looking for, right? So it's a series of techniques to like hunt down the one function that satisfies the thing you want. And it's super useful because in real life, nature often gives you some cryptic formula. It says like, oh, like this ball will follow the law of gravity. Okay, great, that's very nice. Where is the ball going to end up? Is it going to hit me in the face? That's why we do differential equations. So how do we hunt down these functions? Okay, what else we got? Differential geometry. Differential geometry, I would say, is about the differential part. Is how do you describe objects using functions, right? So this is a beautiful example. Differential geometry. Differential geometry. So, for example, if you have a sphere, and you're like, how am I going to describe this sphere to somebody? Or maybe I have a funny donut or something. The differential geometry, the core thing in differential geometry is something called a diffeomorphism. A diffeomorphism. And this is a map that preserves the structure that you want, the geometry that you want. And for example, if I have a sphere, I can make a diffeomorphism from most of the sphere to the ordinary plane. So I can map the ordinary plane in R2 that everybody knows, and I can map it to a sphere, okay? And I can make this map. And the map is almost perfect, except there's one problem. Does anyone know what the one problem? If you try to make a function that maps the plane to a sphere, this is actually the original map maker's problem, right? I have the globe and I want to make a map of it. What is the problem going to be? Yeah. The poles, yeah, exactly. If you make a map like this, you can prove that it's impossible to make a map from R2 to the entire sphere. You must miss some points. And one simple way to do it is to skip the South Pole and North Pole. So minus, subtract the South and North Pole. And so in differential geometry, you make something called an atlas. And you don't just have one map, you have many maps that smoothly fit together to cover the whole space. So you cover it, you cannot cover the plane with just one map, but you can cover it with two maps. So you can have a second function, this can be your phi1, and this can be your phi2, that can cover the rest of the sphere, missing maybe, say, 2 points on the equator. So you can take two points over here on the equator, and you want to make sure that these two things smoothly fit together. You want to make sure that the composition of phi1 and phi2 inverse is a smooth function, is differentiable, and all that. That is the differential in differential geometry. So differential geometry, I think, is how do we describe shapes using functions? It really is fundamentally about functions. Let's see, do we have any other good ones on here? Okay, more differential equations, calculus, differential equations. Complex analysis is about functions of these complex variables. And it turns out, right, functions of complex variables are way nicer than functions of real variables. I can't tell you why that is. There's something nice about the complex numbers. But complex analysis is really, can we study the functions of complex variables and how are they different than the functions of real variables? Okay, complex analysis. And then you get, e.g., holomorphic functions are nice functions, and things like that. So how are functions of a complex variable? Once you do that, you can get quite nice things that you don't get of a real variable. Okay. All right, real. Okay. This person didn't do what I wanted. I don't know what course that is. Okay. Topics in modeling and optimization. This is a great one, right? In real life, you have these real life problems, and what you want to do is you want to turn them into a math problem, and that problem will often be about functions. In modeling and optimization in particular, you're like, how do we find the maximum of some function, right? We have some function that tells me how good or bad a solution is, and optimization is, let's find the maximum of the function, the best possible. So again, that's another one that I think is very plainly about functions. Let me just write optimization because that's super clear. Let's say applied optimization. Optimization. So you take your real life problem, you convert it into functions. Maybe your problem is, how do I find the shortest path on these bunch of routes? Okay, then you say, I'm going to turn that into a problem. So turn it into a problem about a function. I'm going to have a function that measures, turn it into a function problem. And then you can apply all sorts of techniques, find the maximum or minimum. Okay, so that function is sometimes called the objective function. So that's another one I think very plainly about functions. Anyone have one that they think is not about functions? Can you name a course that's not about functions? Yeah. Yeah. Graph theory, yeah. Graph theory also, I think it's the same kind of thing where I said that you have nice ordered sets to nasty things. The things can be graphs. So for example, you can look at the number of ways to color a graph. Coloring a graph is assigning a function, either red, green, or blue, to every single vertex. So again, it's the same kind of thing as combinatorics. So you're looking at these maps where the inputs and outputs are not real numbers, but they are these like objects that you care about. So like graphs, coloring is on graphs. How can we map graphs to graphs? How many different ways are there to interchange the labels on these graphs? Things like that. So same kind of thing. Yeah. Is there another one? Yeah.
What about just set theory?
Set theory. Yes. Okay. Set theory. Set theory. Set theory. Yes. So eventually, if you go very abstract, but even in things like set theory, you have things like you have one construction of the ordinary numbers is you say, oh, I can make a set. I can make the empty set, and then I can make the set of sets, and the set of sets, and so on. And you have functions, like you have the function that is like add one layer, right? And this is called like the successor function of sets. So you take the function f inputs a set of sets, and then like outputs the set of those sets, and this is called the successor function. So things like that. So I think actually, and there's a version of set theory called type theory, where it really is like, let's do set theory with all functions. So you're right, this one, maybe it's less on the face of it, but as soon as you start reading into it, it's going to be functions all the way down. Okay, great. Anyone else? Yeah?
This one kind of might already be obvious, category theory?
Yes, category theory, I think, is the one that is, category theory is like, the thing that we want is functions, and we don't want to think about what the actual things are. So we want to study like functions on their own right. The functions are the first class character. Yes. There's one more I'm hoping someone will say, yeah. Probability theory. Okay, well, that one too. The probability theory. This is an amazing one. This is my favorite, so I did my PhD in probability theory. And in probability theory, the core essential thing are random variables. Random variables. That is the main thing in probability theory. And what is a random variable? You might know that a random variable is a function x from the probability space to whatever you want it to be. Yeah. So every time you're studying random variables, you're actually studying functions. And actually, a lot of this course in particular, we'll see that is going to say things about these functions. Like, when do random variables converge? In what sense? We'll be doing that kind of stuff in this course. So really, probability theory is about functions, and this course is about functions in the same way. Okay. There's one more important course people haven't put on here. Yeah? Logic. Okay, I'm going to put logic in with set theory. There's one more. What's a core undergraduate course that nobody's said so far? Yeah. Linear algebra, that's the one I'm looking for. Okay, linear algebra. Linear algebra. Okay. And linear algebra is also about functions. There are two important types of functions in linear algebra. One of them is matrices. You might say, hey, a matrix, that's a box of numbers. That's not a function. But the core thing in linear algebra is functions that are linear, right? You study linear functions. And so you'll look at maps like M that goes from some vector space, maybe called the input vector space, to the output vector space. And that is what a matrix is. A matrix multiplication is a map from the input space to the output space that is linear. So linear algebra, very, very much about functions. It's just about the linear ones. There is one other thing that is in linear algebra. This is a really funny way of thinking about it. If you have a vector, like you have the vector x1, x2, x3, x4, you might say, hey, that's a vector in R4. That's how you would normally think about it, especially in linear algebra class. But there is one other way you can think about it. You could say, hey, a vector is actually a function that inputs a number, either 1, 2, 3, or 4, and outputs a real number. And if I say, what is the value of your function at 1? That's the first input. What is the value of your function at 2? That's the second input. What is the value of your function at 3? That's the third input. What is the value of your function at 4? That's the fourth input, x4. So a vector is actually a function. It's just that the inputs are very boring, 1, 2, 3, 4, right? This is a funny way of thinking about it, but it will turn out to be useful for our course. Yeah?
Does it map them to R or R4?
Oh, it maps them to R. This is very important. So yeah, let me say exactly what it is. It gives the components. So if I do the vector x and I input the number 1, I want to get the component x1. So every individual component is in R, and I'm thinking of it as a function that inputs which component do you want me to look at and outputs the answer. Okay, so hopefully I've convinced you that all of mathematics is about functions. And now I can tell you sort of what is the point of this course, is we're going to try to look at what can we say about groups of functions in general. So we're not going to look at specific functions, like, for example, in probability theory, maybe you look at some very specific random variables that come from a specific way, or like stats class, or in calculus, it's a good example. You'll look at like, oh, like this function has a derivative that's positive here, and you're looking at one specific function. In this class, we're going to look at all of the functions sort of all at once, and say, if we have a whole group of functions, what can we say about them sort of as an ensemble? Like, what properties can we say about functions as a group, as a big collection? So this is the idea of this course. So some people would call this functional analysis, and really this course is an introduction to functional analysis. And so functional means the things that we care about are functions. We're going to look at big sets of functions. So our objects will be sets of functions, collections of functions. And analysis means we're going to look at when do things inside the sets get close to other things. Okay, so analysis is like measuring how close they are, when do they get close, things like that. So ideas of convergence amongst these sets. So maybe in your previous course, you talked about metric spaces, and you're like, oh, you have the points in a metric space. And probably your brain was like, okay, it's like you have some blob, and then the points are like little dots, right? Like on a page, they're little dots on the page. In our course, the points will be functions. Every single point will be a function, and then we'll talk about, oh, these functions get close to that function. These functions are not close to that function. These functions are close to this other function in this sense, but not in this other sense. Those are the types of things we're going to do. So in some sense, it is a big kind of zooming out of what you've done in previous courses. It's a zooming out of calculus or real analysis, where you say, we're going to think of the functions as the thing. We're not going to look at specific functions. We're going to look at the whole group of them and see what can we pull out of that. And I'll give you some specific examples. And in particular, we'll get to our main quest, hopefully, by the end of this class. The main thing that we're going to try to get to that is going to come out of this kind of analysis. Okay. Oh, yes, I have a fun quote for you that I read this many years ago, and it has stuck with me. So I thought I would read it to you guys. And this is the idea of the power of this idea of zooming out in mathematics, and why can you get stuff from it. I think this is really why math is beautiful and works. Okay, here let me just read this out loud to you. Imagine a clockmaker who somehow has been oblivious all his life to the many simple rules of physics. One day he accidentally drops a clock, which to his surprise falls to the ground. Curious, he tries it again, this time on purpose. He drops another clock. It falls to the ground. And another. Well, this is a wondrous thing indeed. What is it about clocks, he wonders, that makes them fall to the ground? He thought he'd understood quite a bit about the workings of clocks, but apparently he does not understand them well enough. He does not understand them quite as well as he thought he did, because he's quite unable to explain this whole falling thing. So he plunges himself into a deeper study of the minutiae of gears and springs and winding mechanisms, looking for the key feature that causes the clock to fall. So he's taking apart the clocks. He's like, oh, maybe it's this gear that causes the clock to fall. It should go without saying that our clockmaker is on the wrong track. A better strategy for this problem would be to forget all about the inner workings of clocks and ask, what else falls when you drop it? A little observation will then reveal that the answer is pretty much everything, or maybe everything that's heavier than air. Armed with this knowledge, our clockmaker is poised to discover something about the laws of gravity. So the idea of this paragraph is telling you sometimes in mathematics, if you get too hung up on the individual details, you will kind of miss the big picture, right? And we don't want to be looking at individual functions too closely. We want to look at all the functions all together at once to see what is true about collections of families of functions in general and what we can derive from that, right? So it's a little bit like zooming out and seeing what's going on. I think this is kind of true about all of math. Like, why is math powerful? Because you do math one time and then you apply it in all sorts of different cases. So really, this is like the power of math. I think this was actually written about algebra, but we'll use it for our studying functions. Okay, this is great. I'm about to make my second point, but this is a good place to stop for questions about the first point. Everything is functions, and we're going to look at families of functions and try to understand math that way. Okay, the second point, right? Now that I've convinced you that everything is functions, and that we want to look at functions like this. Point number two. Point number two. What are functions? Functions are fancy vectors. Functions are actually vectors, and they're just fancy vectors. Why are functions fancy vectors? Well, I showed you a second ago that a vector is just a function with a stupid input, right? Vectors in R4 are inputs where there's 4 possible inputs. What is a function? Let's say a function from 0, 1, a function from 0, 1 to R. You should think of it as a vector. You know, it's the vector. You got f of 0, you got f of 0.1, you got f of 0.2, you got f of 0.3. Okay, you're going to be here for a while because it's an infinite list, and it's not even countable, so you can't even write them down the way I did. But fundamentally, it's like a list of numbers. What are all the outputs of f? Okay, so this is like a vector, but the problem is it's not a finite dimensional vector. It's not 4-dimensional. This is an infinite dimensional vector. So if you want, maybe fancy could be replaced with infinite dimensional. Infinite dimensional. And sometimes, like in this example, not only is it infinite dimensional, it's an uncountable dimension. Super huge infinity. And more fundamentally than that, I can defend this point that functions are fancy vectors by pointing out that functions do 2 things. What are 2 things you can do with vectors and 2 things you can do with functions? The 2 things you can always do, So no matter how weirdo functions you're looking at, there's 2 operations that you can do to functions. Or I guess they have to be functions into R or C or something. So functions whose output is R. So maybe always is, maybe take that, make sure you know this little detail. Always. Functions with outputs. Let's say in R. And the 2 things you can always do, you can add together functions. Add them together. So you have some function f, you have some function g, and maybe there's some weirdo, nasty functions, but as long as they output things in R, you can make a new function called f plus g, f plus g. And the definition of f plus g is that f plus g of x equals f of x plus g of x. So whatever f did and whatever g did, just add those together, and then you get this new function called f plus g. And you can always do that. No matter what a weirdo functions you're looking at, you can add them together. And the other thing you can do is scalar multiply them. Scalar multiply them. Okay, so if you have some function, f. You have some function f, and you have some number, I'm going to call lambda. I'm going to use Greek letters for our numbers. So f is in R, and f is some weirdo function from some maybe complicated space to R. I can make a new function called lambda f, and the rule is lambda f of x equals whatever f of x was, take that and multiply it by lambda. That is the definition of lambda times f. So you can, no matter what weird functions you have, you can always add them, and you can always scalar multiply them. When you have things that you can add them together and scalar multiply, like functions, in math, we give that a name. Does anyone know the name we give to things that you can scalar multiply and add together? Yes? Vectors. Yeah, we call these things vectors. Anytime something you can add them together and scalar multiply them, we call them vectors. And this really is going back to my point that functions are just fancy vectors, right? There's another way to think of functions are fancy vectors. What are vectors? Vectors are things you can add and scalar multiply, and functions, you can do just that. So really, this second point, the first point tells me what we're doing and why we want to do it, and the second point tells me how we're going to do it. And what we're going to do is we're going to take everything we did in linear algebra class, and we're going to mash it together with everything we did in analysis class. So this is the kind of the picture that we're going to get from this kind of argument. We have the linear algebra class world, and linear algebra class is about linear vector spaces that are finite dimensional, that have like 4 dimensions. You can write down as a box of numbers with 4 things, or 4 by 4 matrices. That's linear algebra. And then we're going to take analysis, real analysis, that is about things getting close together. And we're going to mash them together, and we're going to say we're going to study functions like in real analysis, but we're going to use some of the tools from linear algebra, and we're going to think of functions as fancy vectors. So this will be our functional analysis. Okay. And this is absolutely devastating news for a lot of people in the class, because I think a lot of people don't like linear algebra. There will be a lot of thinking of things the way we think of them in linear algebra. It really is a mix of linear algebra and real analysis. And to gauge your level of interest in in linear algebra, I have another mathematized question, which is, using emojis only, how do you feel about linear algebra? So you can, hopefully you can get in through this code if you haven't gotten in. I also have a good answer for this one, so I'm gonna do it as well. Give me your emojis. Okay, and then it'll be a fun game for you guys to figure out which one is mine. Okay, we're gonna display everyone's thing, and then we'll see what it is. Okay, 22. We have about. Okay, I'm gonna stop it in like 1 second here. I think we have enough answers. Okay, reveal. Ha! Okay, amazing. Okay, let's see. Gonna make this. Hey, that's not as bad as I thought it would be. Okay, this is great. Okay, we got some melting emojis. This is your brain melting. This is a sad flower. Heart plus heart breaking. The heart is impressive. I think most people would be on heart breaking. And then we have an ice. This is a long sequence. I cannot. Oh, goat. A goat is a good thing, right? Oh, somebody really likes Leon. This is amazing. Okay, great. We have the black heart. Very nice. Okay, so some people like and some people don't like linear algebra. Does anyone know which one is mine, or have a guess which one is mine? You take a guess. It's okay to be wrong. Yeah, what do you think?
Heart and heartbreak?
Heart and heartbreak? Nope. No, that wasn't me. Yeah.
The one that's swearing.
The one? Nope, that wasn't me either. No. No, yeah.
Isn't the confused one the saddish face and then rolling the eyes?
Nope, that's not me either. Yeah. Yeah.
Is it the gun to the head?
It is not the gun to the head. It is not the gun to the head. I will reveal I was the broccoli. I'm the broccoli. Why is linear algebra like broccoli? Well, when you're an undergraduate student and you take linear algebra, you're like, what the hell is the point of this? And it's just like eating your vegetables, right? Somebody tells you, you got to eat this. This is be healthy for you. To get a degree in math, you got to eat your vegetables and do linear algebra. That's just what you got to do. And you're like, fine. And you like eat it. You're like, what's the point? Like, I don't really get it. Sometimes vegetables are tasty and it's good. And other times you're like, well, I'm just eating this because they told me to eat my vegetables. And that is how I feel about linear algebra. When I was an undergrad, I was like, there's no point. Like, what are we doing here? Like, okay, fine. I like learned it all, but like, why? And the problem with linear algebra is that it's so useful that they want to teach it to everybody before you see what it's useful for. But in this course, we're going to see what it's useful for. So we're going to have a cool theorem by the end of today that will explain to you why we made you eat your veggies in linear algebra class. It's to do cool stuff like we're going to do today. Another example is the course I previously taught on Markov chains. If you saw that course, you know that there was a lot of linear algebra as well. And linear algebra is like, it's like the bedrock of like how everything works essentially. But you don't see it in linear algebra class because they just make you eat your vegetables and they're like, in a later course, you will use the linear algebra and then they will explain why it's useful. This is the later course. So even if you don't like linear algebra, hopefully you can get some payoff from that. Okay, and to start with, I'm gonna have us do a little like review linear algebra problem, a review problem from linear algebra. And that review problem is gonna directly lead into our main quest for the course. And so the review problem has nothing to do with functions or functional analysis, but it will have an analogy to what we'll do later. Okay, and here's the review problem. Vector problem 1. Okay, let A, B, and C be these three vectors. A is the vector of all ones, B is 1, 1, minus 1, minus 1, C is 1, minus 1, 1, minus 1. Very, very nice vectors. Suppose we want to write the vector x, which is 10, 20, 30, 40, as a linear combination of these vectors. This is exactly the kind of thing that they would do in a linear algebra class. They would say, look, we just want to write x like this. Don't worry about why. We'll explain why later, but for now you have to just believe me that there is some good reason to do it. I did one of the values for you. I said alpha is 25, but you guys have to figure out what would beta and gamma be. And there is a hint, which is A, B, and C are not just some weirdo random vectors off the street. There's a nice pattern in A, B, and C. A, B, and C do something nice altogether. So if you had a good linear algebra course, you will see right away what it is. If you had a kind of so-so linear algebra course, maybe you can shake off some rust and try to remember what is the trick. But I'll give you guys maybe like five or 10 minutes to work on this. Let's say 5 minutes. I think that'll be a good amount. Try to figure out what is beta and gamma, and try to remember what could possibly be special about A, B, and C here that is really useful for doing this kind of thing. Okay. there's like 40 seconds left. Put in whatever guess you have for maybe you only know beta, and you can just put that in. If you have no idea, that's also fine too. I know there's approximately 26 people, so if you don't answer, that's okay here. And we'll see how many people got it, and then maybe I'll give some hints to help us figure it out. Okay, let's take a look here. Let's see, is there a consensus? Is there one common answer? Some people said 10, some people said minus 10. Actually, only one person said 10, so everybody who answered said minus 10, but that's only about half the class that answered. And I think minus 10 is the right answer. But let's talk about what is this special property. Does anyone want to share what special property they used? Yeah.
They're orthogonal.
They're orthogonal. That's a fancy word. What does that mean?
Well, with respect to the dot product.
Yes. Okay.
The dot product between any pair of them, it should be 0.
Yes, that's right. That's exactly the thing that is the trick to unlock this whole problem, is that the vectors A and B are orthogonal to each other. And orthogonal means if you do their dot product, so their dot product is you do the entry-wise product of the entries. Let's write this down. So we got A, which is the vector 1, 1, 1, 1. We got the vector B. Was B the alternating one, or was B the 1, 1, negative 1? Negative 1. Okay, perfect. And you do A dot B. Some people write A dot B. They would write A inner product B like this. Those things are equal. And they just mean 1 times 1. So you match the entries. 1 times 1. And then you do 1 times 1 again. Plus 1 times 1. And then you do 1 times minus 1, right? Because the B has these minus 1s in the third and the fourth entry. And if you add this all up, 1 plus 1 is 2, but minus 1 plus minus 1 is minus 2, and it exactly cancels out. These things are orthogonal. So that is what orthogonal means. Their inner product is 0. For vectors in like R3, this is the same as perpendicular, right? You can kind of imagine them, and you know they're at 90 degrees to each other. These are vectors in R4, so you have to maybe imagine more broadly. That's why we say orthogonal instead of perpendicular. Some people would still say perpendicular. And this is a useful property. You're saying, why is it a useful property? Can anyone explain how this is useful for the question at hand, or how it was used? Or maybe the 15 people who got it right did it a completely different way. I don't know. Yeah.
I looked at like the top and bottom as like if you add them together, and put it out as if you like subtract.
Okay, so you started with the vector x, I guess. So x was what, 10, 20, 30, 40. Okay, and then what do you mean by you look at the
Looking at like B and C, I guess.
uh-huh.
And then the top like entries of B and C, I guess, like when you multiply them by the variables, then they have to like equal 10, and then like the middle one.
Yes, okay. So I think you did a straight linear system. So if you take x equals alpha A plus beta B plus gamma C, and let me add in my vectors. You're saying if you look at the top entry of this, look at top entry, you get an equation, and the equation says 10 equals alpha times 1 plus beta times 1 plus gamma times also 1. Is that right? Yeah. So this is the sort of classical way to do it, is to convert this into a linear system. You actually have 4 of these equations, right? So you got 10, 20, and 30, 40. And you only use 2 of them. Okay. Alpha, I guess this one would be alpha times 1 plus beta times 1. And this one is minus gamma, or plus gamma times minus 1. And then this one, alpha times 1, because alpha is all 1s. But this is a minus beta, and this is a plus gamma. And then this one is an alpha minus beta minus gamma. Okay. And yeah, so you just took the system and you did like the classical, like crunch it together. This is a totally valid solution. This is the hard work way to do it. It's a very valid way to do it. There's nothing wrong with it. But there is a shortcut using the orthogonal. Yeah.
Can you dot product both sides of beta?
Yes, this is the idea. So this is the honest, hard-working way. It's just like, look at the entries. By the way, looking at the entries is dot producting with specific vectors as well. Look at the top entry is the dot product of x with the vector 1, 0, 0, 0. So if you do the dot product with the vector which has a 1 in the first component and then zeros everywhere else, then x dot product with that is just 10, because the zeros kill the 20 through 20, 30, and 40. And then the zeros also kill everything except this. So like looking at the entries is actually a dot product with the specific vectors that are a 1 in the component and zeros. Like components are actually dot products. And the idea is, the trick is don't do the dot product with these coordinate vectors, which the coordinate vectors are sort of the way the problem was stated, but maybe they're not the nicest thing to work in. Instead, let's do the dot product with one of the specific vectors we have. Do the dot product with, and which vector did you suggest? You did
Beta or gamma, or the B or C.
B or C. Let's do B. Okay, great. Let's do B. Dot product with B. So if you take the equation, you do the dot product of both sides, that's still a true equation. So x inner product B, and then that's the inner product of alpha A plus beta B plus gamma C, all with B, right? So I take my equation, these two things are equal, so the dot product with beta, or with B is equal. And now I can use a nice formula, which is the linearity of the dot product. Alpha A plus beta B dot product with B is the same as alpha times the dot product A and B plus beta times the dot product B and B. I can expand it out. So this is called linearity of the dot product. Linearity of dot product. Okay, and let me write this out. Let's put the alphas on the outside. Beta, gamma, and then we have A times B plus B dot product B plus C dot product B. Okay. Who remembers this from linear algebra class? Now that I've shown it, you're like, oh, I vaguely remember doing this in linear algebra. Who has never seen this before? Okay. Most people are unsure if they've seen it before or not, which is good. Okay, you probably have seen it, but just like you're rusty, that's okay. And the nice thing about this is that these dot products are, again, they're not just some arbitrary thing. They are some very special dot products. The dot product A with B, we did already. A with B was 0. 0 is a nice number because whatever alpha is, it goes away in this equation. So this is alpha times 0. Okay. Beta is still there. What is B inner product with B? The inner product of B with B, that has a name. Yeah, or maybe you just calculated it.
The norm squared.
It's the norm squared. So this is the length of the vector. When you inner product something with itself, that is the norm squared. You might remember this from the Pythagorean theorem. This is 1 squared plus 1 squared plus minus 1 squared plus minus 1 squared. You square all the entries and add them together. Why is it squaring? Because you multiply it by itself, right? And that's the norm squared, the length of the vector squared. In this case, that's 4. 4. So you get B times 4. And we didn't do this one, but the C inner product with B will also be 0. Right? C is alternating, so it'll be plus 1 minus 1 plus 1 minus 1, and it'll cancel out to give 0 at the end. So that one's 0. And this is a beautiful thing, because we have these zeros. If it was like times 1, that wouldn't really help us. Right? We would still have, if the inner product worked out to 1, then we would be back into some equation like this. But because the inner products are 0, it dramatically simplifies, right? We have all these zeros, things cancel out, and you get beta times 4. Times 4, also known as 4 beta. And what is 4 beta? It's the inner product between x and b. The inner product between x and b I can do in one line. It is 10 times 1 plus 20 times 1 plus 30 times minus 1 plus 40 times minus 1. In other words, it's the sum of the first two minus the sum of the last two. 10 plus 20 is 30. Subtract the 30, get to 0. You get minus 40. So this is minus 40. So minus 40 equals 4 beta, and therefore beta equals minus 10 is the answer, which people found. Okay, that's the shortcut way. If you kind of know the trick, you can do this calculation extremely quickly. We did it a little bit slower to show you the steps. And the point I wanted to show you is that it's faster than this way. So how many people did it the classic, slow way? Okay, everybody. Did anybody do it the sneaky, fast way? Nobody. Okay, great. We're learning something then. So the sneaky, fast way, you do it right away. Why don't I give everybody a minute to calculate gamma, okay? It should take you like, if you know the trick, Doing it with gamma should take like 10 seconds or something, but I'll give you a full minute, and I won't open a Mathmatize or something. I'll just pause and wait. What is gamma? Gamma equals. Okay. Let's check. I'm curious. Before we did the trick, did people do it the classical way? Is there some answers for gamma, or was that? So people had -5 for gamma. Let's see if we could get -5. And again, use the starting place. Let's not jump to the answer. The starting place is the equation x equals alpha a plus beta b plus gamma c. And we take the inner product of both sides with c this time. So we get the inner product of x and c is alpha times ac plus beta times bc plus gamma times cc. Okay, I kind of did the step of expanding it out all at once. But the inner product of x with c is the inner product of all this stuff with c. And then by expanding it out by linearity, you get this nice sum. A bunch of these are 0. A and c together is 0. That's because c alternates and a is the sum. B and c we said was 0 already. That one's 0. That just goes away. And what is c with c? This is the norm, the Euclidean norm of c squared, which is 4. 1 plus -1 squared plus -1 squared plus 1 squared plus -1 squared is 4. So this equation gives you that the inner product of x with c is equal to 4 gamma. And on the other hand, the inner product with x with c is 10, 20, 30, 40 with 1, -1, 1, -1. Okay, so that is 10 minus 20 plus 30 minus 40 equals 4 gamma. And then we gotta work this out. So we're subtracting 60, we're adding 40, so I get minus 20 equals 4 gamma, and therefore gamma equals -5, which is what people got the old-fashioned way. Okay, so the point is that it should be relatively quick once you've made this observation about orthogonality, and using these inner products, you can squeeze information out quite quickly, and it's quite useful. Another way to say this same stuff in the linear algebra way is you would say, don't work in the ordinary basis, work in the basis that includes a, b, and c. So this is a kind of a change of basis idea, which is we don't want to think about the vectors with their components. We don't think about them component-wise, as what is the first component, second component, third component, and fourth component. We think of how much is in the a direction, how much is in the b direction, how much is in the c direction. So we're working with that as part of our basis. That will let us calculate things more easily. Okay. So this is the kind of stuff you do in a good linear algebra course with inner products and stuff. Okay. That was the warm-up linear algebra problem. I'm going to give you the function version of this problem, but this is a good place to pause for questions. Okay, let's see the analysis version of this problem, which is, here it is. So I have functions now, not vectors, but of course, you know now, functions are fancy vectors. We're working on the interval x between -pi and pi, and I want to write the function f, which is this crazy looking indicator function. Let's draw on the board what this function looks like. So what is this function? It's 1 if you're between -pi/2 and +pi/2. So there's pi/2 and -pi/2. Here's the x and the y axis. And the function I'm thinking of, let me see, did I bring some chalk? The function I'm thinking of, it's 1 in this interval, okay? And then did I do less? I said less than, okay. It's got some circles like here. And then it's 0 otherwise, so this looks like this. Nice function. This is called a bump function sometimes. Write it as a linear combination of the cosine functions. Geez, that got intense quick. Okay, gn of x is cosine of nx, some cosine function with frequency n, cosine of nx. We gotta find the coefficients. We're gonna write this function f in orange as an infinite sum, f of x. We have to write f of x equals the infinite sum of the gn's times some alpha n. And our job is to find the coefficients. Wow, a doozy of a problem. Write this function in terms of these functions as an infinite sum. If you've never seen this kind of function before, this seems totally crazy. But you did just see the linear algebra problem that I said was similar. So think about the analogy and think about how would you extract, sort of, if you try to do it as a a linear combination row by row. That's like saying the value at pi over 2 is this, the value at 0 is this, the value at 1 is this. You would be there all day. You would have infinitely many equations with infinitely many variables, right? The alpha n's are infinitely many variables. But there is a trick, and the trick will let you extract the value of the alpha n's exactly as we did. If you've seen this kind of thing before, you might recognize the trick. If you haven't, you have to sort of use your imagination for a little bit and think. I'll let you guys think for like, let's say a minute or 2 minutes, and then you can either say, yes, I can see some kind of relationship, or no, like I'm not seeing what the connection is with the algebra thing we just did. Okay, well, let me give you guys, and feel free to chat with your neighbors or put your hand up if you have a question I can help with. Let's say 2 minutes. Just thinking, what does this problem have to do with the problem we just did? And how can we leverage that? Okay, there's like 20 seconds left. Regardless of which one you pick, I would like you to choose one so that I know the rough numbers, and it will help me sort of pace how we're going here. So put in your answer if you're seeing something or maybe you're not. It's like totally alien. It's good to know. Okay, so I'll leave this open for a second while I sort of talk about this. Let's see, where to start. So, yeah, I guess maybe I will just reveal. Let's see how are we feeling? Okay, all right. 15 people say yes, they see maybe some relationship, and 10 people say no. Of the 15 people, what is like a relation that you see, or like how can we take what we did from the linear algebra problem and get something useful for this crazy function problem? Yeah.
Will you find an inner product where the GNs are orthogonal to each other, then you can do the same method?
Amazing. Okay, yeah, this is exactly the thing that I wanted you to see, which is that if only we have this new problem, and if only we had an inner product, we would be in great shape. So we have gn of x times alpha n, and we're doing the infinite sum, and that's really hard because it's an infinite sum, and this is supposed to be f. But if only we had an inner product, I guess let me write this the other way so that I can do it. If only we had an inner product we could do. We don't know what an inner product means for functions. What could that possibly mean? But if we had one, and we could do the inner product with gn of x, then on one side we would get this, and on the other side we would get the inner product f of x with gn of x. So if we can find some kind of inner product, and then take the inner product of both sides, and then also if we make sure that the inner product is the same kind of thing as before, where all the gn's are orthogonal, then this crazy infinite sum will simplify down to just one number. It'll simplify down to a bunch of zeros, so you get 0 plus 0 plus 0, infinitely many zeros, and then you'll get one number, alpha n, times gn with itself. Oh, okay. This is a pet peeve of mine. I'm using gn as the index I did the thing with, but then gn is also the index in the sum, and this is a little bit annoying. Let me relabel. Let's do the sum with j, so that it is a little bit more technically correct. Hopefully this doesn't bother anybody. Alpha j. Okay. So it's the infinite sum of all the g's. We pick some particular n, we do the inner product. Almost all of the terms go to 0, just like before. Before, almost all the terms was 2 out of 3. Now it's infinity out of infinity terms go to 0. And we're left with one term. And then, if we can look, we have one equation, alpha n times something equals something, we can figure it out. So the only obstacle is, what is the inner product that makes the g's orthogonal? So this is the big question. What is the inner product? Okay, so we need some kind of inner product where we can do the inner product not of vectors, but of functions. Yeah, what do you think?
Do you want it?
Yeah, give it to me.
It's the integral from negative pi to pi where you multiply the two.
Okay, so the inner product of f and g will be the integral from minus pi to pi, and then what do you want to do?
Multiply them together.
Multiply them together, like f, g, like that. Is that
dx.
dx?
Yeah.
Okay, then should I plug in like f of x and g of x? When you say multiply them together, you don't mean multiply the functions together. What do you
No,
mean?
I mean f of x.
F of x times g of x. Okay, very good.
So it's point-wise, but
Got it. Got it. So f and g are functions, right? And we can evaluate the functions at any point. And what Finn is telling us is take the value at x, multiply f of x times g of x, integrate it. Integration. You might remember a second ago I said what is the inner product between a and b. A second ago I was saying it's a1 b1 plus a2 b2 plus a3 b3 plus a4 b4. And if you know what an integral is, you might recognize that these things are kind of similar. An integral is kind of some kind of infinite sum type thing, right? And we're, instead of adding up all the entries, we're adding up all the entries, but now there's infinitely many entries, so we don't add them, we integrate them. So this integral that has been written down is exactly the right answer. And it is kind of the analogy of thinking of vectors, or thinking of functions as vectors, or vectors are actually just functions. It's exactly the same thing. And you'll notice, right, when I said vectors are fancy functions all the way back here, I was like, just list them all out. And so if you do the inner product of listing them all out, you'll get a whole list, and then the only thing you got to do is instead of adding up infinitely many things, you integrate infinitely many things. So it really is the analog of what we did before. This is sometimes called the L2 integral, and a big part of this course is going to be making sense of this L2 inner product. I said integral, L2 inner product. This is the L2 inner product. Inner product. So some people would write the inner product L2. This is the ordinary Euclidean inner product on R4. Okay, and the L2 inner product is multiply the functions together pointwise, integrate it. Okay, so who has seen this kind of integral thing before? If you took PDs, you maybe saw it near the end. Some people have seen it. You might also know a fancy name for this kind of thing. So when you write the function f, equals the sum of the g's, the infinite sum of the g's, alpha n times gn of x. This also has a name. It's named after a famous dead mathematician whose name starts with a number. Does anyone know what it is? Yeah. Yeah. So if you're Canadian, you pronounce it correctly and you say Fourier. But if you're American, you pronounce it incorrectly and you say Fourier. We're going to do the Canadian pronunciation. So it's a Fourier series. This is the Fourier series. And what I'm trying to tell you is that the Fourier series is just a fancy version of writing a vector in a different basis. We're writing the function f, which is a fancy vector. We're not thinking of it as component-wise, what is the value at 0, what is the value at 1. We're thinking about it, how much of f lives in the g1 direction? How much of f lives in the g2 direction? It's a change of basis. This is a Fourier series, and it has all sorts of useful applications. Maybe I'll pause here for questions. Questions, comments? Okay. All right, let's see. How are we doing on time? So let's calculate the alpha n's. I'll give you the formula, right? We essentially had it on the board. What you do is you do the inner product of the equation, this inner product of both sides, and you're going to get an equation. The equation is going to say the inner product of f with gn equals alpha n times the inner product of gn with itself. And these gn's are integrals, or these inner products are integrals. So you get alpha n. What is the inner product of f and g? That's the integral from minus pi to pi of the function f of x times the cosine of nx dx. I have chosen on purpose a beautiful function f. When you're doing the integral of the function f, it's very simple because the function is 0 except for from minus pi over 2 to pi over 2. So you get minus pi over 2 to pi over 2, the integral from minus pi over 2 to pi over 2 of cosine of nx dx. That's a very nice integral. That one you can do. I believe the answer is 1 over n times something. I'm gonna sort of skip some steps. I think it's like minus 1 over n times minus 1 to the power n or something. It goes plus 1, minus 1, plus 1, minus 1 because of a sign. I will leave it as a calculus exercise if you want to figure out exactly what it is. I might have written it wrong here. Let's put a question mark. I don't want to get into some long drawn out thing. Okay, on the other side, you have the integral of cosine squared, minus pi to plus pi. You have cosine of nx times cosine of nx dx. This is alpha n times the integral of cosine squared of nx dx. Does anyone know what that integral is off the top of their head? Yeah.
1 minus cos of 2nx.
You're giving me the antiderivative. Is that what you're saying? You're giving me the antiderivative of this thing? Is that right?
No, I'm just converting it into like a
Oh, I see. Okay. So yeah, you're doing it the calculus way. It's 100% accurate. So to do this integral in a calculus class, you would say, I'm going to do a trig identity, which is I think the one you were doing. You convert cosine squared into a 2 cosine, okay? And then you do the antiderivative, and then you plug in using the fundamental theorem of calculus, and you get the answer. But in fact, for this particular integral from minus pi to pi, there's a sneaky, tricky way to do it. Yeah.
Cos is an even function, so cos times cos
Yeah. Even, yeah.
and you're going from, so it's 0?
No, the odd ones are 0. That's a good. Actually, but you're thinking about it the right way. So what does the cosine squared function look like? Cosine goes up, down, up, down, up, down. So what does cosine squared do? It goes up and down and up and down. So cosine squared looks like this. It goes bloop, 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 bloop. Okay, and we're integrating it from, okay, I gotta do it. Yeah, I gotta do it the other way. We're integrating it from minus pi to pi. So something like this, minus pi to pi. So it's a function that goes between 1 and 0, and it kind of goes in between 1 and 0. And we want to know the area under here. What is the area of this thing? Well, I can tell you for sure it's going to be something between 0 and 1. Does anyone know? Yeah, what? Or the average value will be between 0 and 1. Yeah, do you have an idea?
Oh, no, I was just gonna say the integral is equal to 2 times the integral from 0 to pi.
Yes, that's exactly right. Well, a half. So the point is that this function on average is halfway between. It's exactly halfway. How do I know it's exactly halfway? Because the sine squared function is the other half. So sine squared plus cosine squared is 1. Together, sine squared and cosine squared always are taking up the full thing. So on average, each of them takes up half. You can make this a little bit more rigorous, but for today, we will leave it at this. So the average value is a half. If you took a Math 1200, at the very end of the course, they talk about average values of functions. The average value is 1/2. Sometimes it's above, sometimes it's below, on average, halfway. And so the integral is going to be 1/2 alpha n times the length of the interval, which is 2 pi. So that's alpha n times pi. The norm, the inner product of gn with itself is pi, which is a nice fact. And now I have an equation. 1 over n times some plus minus thing is alpha n times pi. And therefore alpha n is 1 over n minus 1 to the n times 1 over pi. I might have screwed up this part. Let's put a question mark around this because I don't want to check the details because I put it in a computer. So we're just going to plot it in a second anyway. Check. Okay. So we calculated it. It's a 1 over n, and then it has some alternating business. Here is what it looks like on a computer. And so I've done it in Desmos. Let me turn this off and put this into display mode. Here we go. And let's see. Okay. Can people see this? So this is the function f. It's drawn in green here. I drew it in orange on the board, but it's drawn in green over here. And of course, the formula we have, here it is, 2 over pi n times the sine of n pi over 2. That's the sine of n pi over 2 is that alternating bit. Okay. We also, in the thing I just did, we made a mistake when n equals 0. So find the mistake. The answer should be a half when n equals 0. Something funny happens. But let's ignore that for now. Unfortunately, I cannot do an infinite sum on the computer. I can only do a sum up to a large number. And the large number I have chosen is 150. So I'm going to do the sum up to 150. And here is that big sum. This first little bit is the coefficient called alpha n. And the second bit is the function gn, which is the cosine of nx. Let's see, what does that look like? There it is, in red. So once again, you should not expect that this is perfectly equal to f, because I didn't do the infinite sum. I only summed up to 150. Actually, why don't we start at a small number? Let's start at everyone's favorite number 2. Okay, 2. So there's a sum of 2 things, and there's a sum of 3 cosines and 4 cosines and 5 cosines and so on. And as you add more and more, it gets closer and closer to that function in green that we started with. So this is called the Fourier series for the function in green, the function f, and it's a sum of cosines that gets closer and closer to the original function as you add more and more terms. If you did the full infinite sum according to the calculation we just did, you should, in some sense, get f. Okay, so that's the Fourier series. Questions or comments about this so far? Maybe you've seen Fourier series somewhere else. Yeah.
Can you explain the part with, what did you mean about the 0?
Yeah, okay, look. Yes, okay, great. So if you look at the formula, I said the answer was alpha n is 2 over n, and then we did it. But we made a mistake when n equals 0. So it turns out when n equals 0, we did the cosine of nx, and the cosine of nx squared, it does this 1/2 thing, but only when n is 1 or greater. Okay? When n equals 0, you're doing the integral of the function 1. And the average value of the function 1 is not a half, it's 1. So we made a mistake by a factor of 2 when n equals 0. And the mistake was corrected by Past Mihai, who did it properly, but not by Class Mihai, who's more loosey-goosey. Okay, yeah, great. You should check. You should check. All of the stuff is like first year calculus. You can do it. Okay, yeah. So this is the mistake is this should be when n equals 1. This is n greater than or equal to 1. And okay, let's correct the minus 1 to the n. The minus 1 to the n should be the sine of n pi over 2, which I guess is sometimes minus 1, sometimes plus 1, but it's sometimes 0. So let's fix that out as well. It's the sine of n pi over 2. Okay, beautiful. That's the real answer. Okay, this is wrong. This is right. Okay. Yeah, good. Any other questions? Yeah, do correct me if I say things that are wrong. It's good to not be wrong. Okay. Other questions? Okay, so you might say, okay, what is the point of all this? Why do we care? Why are you torturing us with writing this function in terms of cosines? Why it was important? Cosines, it turns out, are extremely nice. So one thing you might do is if you write the function in terms of cosines, you can then solve all sorts of complicated things about the function that you wouldn't be able to do. So a good example is to solve a PDE, so a partial differential equation. We can solve a partial differential equation of the function, starting with the function f. And the partial differential I'm going to show you is something called the heat equation. In the heat equation, you should imagine this is the temperature of an iron bar. So I have an iron bar of length pi. Actually, it's length 2 pi. It goes from minus pi to pi. This is my iron bar. And the middle of the bar, from minus pi over 2 to pi over 2, is at 1,000 degrees. Okay, it's like been in the furnace. The middle piece of the bar is hot, hot, hot. Don't touch it. The ends of the bar are at 0 degrees. They are like ice, okay? And then I take the bar and I let heat happen. Okay, what does heat do? Heat flows from the hot part of the bar to the outside of the bar. So the outside of the bar will suddenly get a lot hotter. As the heat from the middle of the bar flows outwards, it will get hotter. The middle of the bar is going to get cooler. As the heat flows out of the inside of the bar to the outside, the middle should get cooler. But how exactly does it do that? You could imagine if you're designing like an engine or something, this is an important thing to know. This is called the heat equation. And this function over here is the solution to the heat equation. I took g, I wrote it out again, and now I'm saying it's the solution to the heat equation. I just added one little thing at the end. I added this term. E, so x is the exponential function, e to the minus n squared times s. And s is a time variable. So we have this time variable. At time 0, these two things are exactly the same because you have e, you have e to the n squared times 0. E to the 0 is 1. So at time 0, it's exactly our original function. But at time later than 0, what this exponential is going to do is it's going to shrink down. It's like the coefficients are changing over time. We're shrinking down some of the coefficients. Let's see what that looks like. So I'm going to turn this on. So here at time 0, Teal. This is not a nice color. Let's pick a better color. Purple. Yeah, okay. So here, at time 0, it's exactly the thing we had before. But now what happens if time is bigger than 0? Let's see. So this is going to represent, this is the original bar, hot in the middle, cold on the sides. What happens as time progresses? And look at that. It goes like that. Let's do it in slow-mo. Let's go only up to time 1 so we can see. Okay, let me do like 100 modes because I think the computer is starting to melt. Okay. So very quickly, the heat moves out and slowly dissipates. And this is the kind of thing you can do with a Fourier series. It turns out you can answer all sorts of questions like this. How does the heat move out of here? So yeah, who's heard of the heat equation before? Okay, everyone who's taken PDEs has heard of it. We have a nice solution to the heat equation. Here's another one. This is the solution to the wave equation. And the only thing I did is I took our Fourier series from before. Instead of putting an exponential, I put in a cosine of n times s. And what does that look like? At time 0, it's the original thing. Let's make it a fun color again. Let's go purple again. And now, as time moves on, the waves travel around. So yeah, we can make time go even longer. So the waves will bounce off each other and do all sorts of things. So this is the solution to a wave equation. If you have a piece of string and you lift up the middle of the string and then let go, it will bounce around like this. And these little smidges, splotches are because I'm doing a finite sum up to the first few terms, but not all the terms. Okay, so these are some applications of the Fourier series. We're not going to do the applications in this course, but we're going to work on the actual Fourier series itself. So you don't need to know anything about PDEs to understand this course. This is just a nice motivating example and some fun pictures. Okay, any questions or comments here? Okay, and this brings me to the main question in the course, the main quest. The main quest. Okay, and to tell you what the main quest is, to show you why it's like a real quest and it's not like some silly thing, like, oh, of course it'll be true. I want to go back to the algebra problem, okay? So here is the algebra problem. So A, B, and C were the vectors from the last problem. So the 1, 1, 1, the 1, 1, minus 1, minus 1, the 1, minus 1, 1, minus 1, and we solved it for 10, 20, 30, 40. We said x equals 10, 20, 30, 40. We figured out what does alpha, beta, and gamma have to be. That was what we did. Okay, right? We did that up here. We solved. We said gamma has to be minus 5, beta has to be minus 10, and if you add it all up, you will get that 10, 20, 30, 40 equals the sum of the things that we said. But now the question is, what is it always true? Could we always do that for any x? We had some vector x. Is it always true? I will let you think for a moment. All right, let's do 1 minute here. Give me your gut instinct. Again, if you had a good linear algebra class, there's a simple counting argument here that will reveal the answer. Okay, let's see what your guesses are. Maybe you figured this out by counting. You don't even have to count very high. All right, what do people say? Okay, everyone has figured, or most people have figured out, no, it's only true for special values of x. There's a very simple reason. Does anyone want to say why? Yeah.
They don't form a basis of R4, they don't span it.
Yes, so A, B, and C, they do not cover all of R4. The proper term is span, exactly like you said. A, B, and C do not span R4, so if you do linear combinations of A, B, and C, you won't get R4. Why? How can you know for sure that they don't span R4? Yeah. There's only 3 of them. R4 is a 4-dimensional space. You need 4 basis vectors to do it. That's maybe one of the key things in linear algebra. So just by counting, we can say, look, this is 3-dimensional. R4 is 4-dimensional, you're going to miss something. You cannot cover a 4-dimensional space with 3 dimensions. Now let's go back to our problem, okay? I'm going to say which functions, so we had this specific function f. We say which functions can we cover? Which functions f can be written as f of x equals this kind of infinite sum, n equals 1 to infinity of cosine of nx, okay? And again, the issue is we might be missing something. In the linear algebra example, we're missing one vector. There's a vector d, which is orthogonal to a, b, and c, that should be there. If you had the vector d, then you could do it for all the vectors and you would be happy. And you can say, look, this is 3-dimensional. If we had one more vector, it would be 4-dimensional, and then we can make sure that it all works. But the problem is, now we're in infinite dimensionals, and infinities are weird. So this one is infinite dimensional. This thing is infinite dimensional. Did we get them all or not, right? Like, is our infinite big enough or not? There's actually another way to say it is, are there functions that are orthogonal even to these things, right? Can anyone think of some other functions that we could maybe put on here that we missed, that we could add on? Well, I'll spoil it. We forgot the sine function. So we should also do sine of nx. It turns out the sine functions are also valid. If you do all the cosines and all the sines, now you're more in business and you're kind of not missing anything in some sense. But how do you know? Like, which functions can we do? How can we be sure we're not missing any? So which functions? How can we be sure sines and cosines covers it? How can we... Maybe there's some weirdo function out there that sines, cosines cover. Or, yeah, the proper term is span. Let me not say span, actually, because it's a little tricky when you get to infinite dimensions. And then last but not least, these are actually limits, right? When you do an infinite sum, we're not actually saying add them up infinitely. We're doing some kind of limit. So in what sense is the limit true? In what sense? What does a limit mean here? Right? So the left-hand side is some honest to goodness function f, but the right-hand side is actually a limit because it has an infinite sum, and infinite sums are always limits. So what does it mean? What kind of convergence are we talking about here? For what functions does it converge? Does it converge nicely? And so on. So this is a whole area of mathematics called harmonic analysis, and we're going to kind of do the very basics of it in this course. That'll be the final boss of the course will be to do this. And everything we do along the way, we're going to build up towards it. We're going to see things, for example, over here, when we were doing this inner product, we did the integral. And we were just like, oh, the integral, that's fine. But it turns out the integral that you learned, the Riemann integral, is not good for this kind of thing. The Riemann integral will not work. It has to be a fancier kind of integral called the Lebesgue integral. And the Lebesgue integral is needed to make sense of limits. Limits of Riemann integrals, turns out, don't work. So we're going to need to fix. So on our way to proving this, we're going to need something called the Lebesgue integral. And so that'll be chapter 2 of the course. And then chapter 3, we're going to do exactly the kind of stuff we did today. Chapter 1 is where we're going to start. And chapter 1 is your first at-home Thursday to Tuesday reading thing. And so that is up now. I will make it live shortly. At the end of what you do this weekend and on Monday, so at the end of your Thursday to Tuesday video watching, you should be able to prove these 3 things. The things that you're going to do are about making everything I said today kind of rigorous. We're going to go, definition 1 is like, what does it mean for a function to be a vector space? What is a vector space anyway? Those are the definitions that we're doing. And you're going to be able to answer these questions. A convergent sequence has a unique limit. On Tuesday, you did that problem with sequences in R. Here they're talking about sequences of vectors. What does it mean for a convergent sequence of vectors to have a unique limit? If xn converges to x and y converges to y, then xn plus yn converges to x plus y. You guys did that on Tuesday. That was in R. And after today, you should be able to do it. After you watch the videos, you should be able to do it in an arbitrary normed vector space. So these are the exercises you'll do after. They should, as the textbook says, these properties can be proved the same way as in the case of convergence in R. And this is kind of like the easiest possible thing you can do. Last time I taught the course, this was the first problem on the midterm, was one of these 3. So watch the videos, Make sure you watch them. There's going to be a really short quiz at the beginning before our activities on Tuesday. Try to do these exercises. If you can't do them, that is a sign that you're going to have to do a lot of work to sort of catch up to learn how to do them. This is the sort of like minimum level that we're going to start at, and we're going to build up from there. Okay, I'll be around for questions and comments for a little bit, but otherwise, make sure you watch the videos, and I'll see you on Tuesday for our activities.